So welcome everybody to the first seminar of this year for the Spatial ML seminar series. We had a pause for the holidays in December, but now we're going to be back to the normal schedule. So it's always going to be the fourth Tuesday of the month is a new seminar for every session. So today I'm happy that we have Marta Andronic. She is a PhD student at Imperial College London in the George Constantinidis group. Her research is all about thinking of how deep neural networks should be implemented on FPGAs for ultra-low latency applications. And she focuses on a special type of neural networks that is actually built and trained out of FPGA LUTs. So it's a very interesting topic that she is going to cover today in her talk. And this talk was actually part of the FPT conference that happened in December, or at least part of this talk, and won a Best Paper Award in that conference. So it's a very interesting topic and a very interesting talk by Marta. The floor is yours.
Yeah. Thanks, Andrew. Hello, everyone. Today I'm going to present our paper called PolyLUT, Learning Piecewise Polynomials for Ultra-Low Latency FPGA LUT-based Inference. The scope of our work is to enable edge AI applications that require ultra-low latency processing and highly lightweight on-chip implementations. Ultra-low latency deep neural networks enhance experimental discoveries, for example, at CERN's Large Hadron Collider. They find application in cybersecurity, particularly in network intrusion detection systems. And they can also find application in real-time image classification. However, the deployment of deep learning models on the edge has proven to be a challenging task due to models' high computational cost. In order to combat this, specialized systems are engineered through hardware-software codesign. Hardware-software codesign involves the development loop between algorithm design, training, and implementation. Compression techniques are also often employed to reduce the high computational cost of neural networks. For example, pruning. Pruning involves the removal of redundant operations, and quantization, which reduces the precision from 32-bit floating point to various lower bit representations, even down to the extreme case, which is binary. Parallelization is another technique often utilized to increase processing speed. In the design of low-latency FPGA accelerators, there are several common architectural choices that can be made. The first one is the DSP-based approach, as seen in prior works that use HLS4ML. HLS4ML utilizes fixed-point arithmetic and implements the dot product between the feature vector and the weight vector using DSPs. The original publication of Finn and another work by HLS4ML deploy binary neural networks. Through the replacement of the multi-bit multipliers with lightweight XNOR gates, binary neural networks offer an efficient solution that removes the redundancy while maintaining high classification accuracy after retraining. However, binary neural networks are still not perfect for FPGAs. This is because they do not fully leverage the underlying FPGA architecture. In particular, XNOR gates and part of the pop-count logic end up mapped on K input LUTs, which are capable of implementing arbitrary Boolean functions. Prior works that use LUTs as more than just XNOR operations are LUT-net, NALA-net, and LogicNets. Our work, PolyLUT, also lies in this category. Let's now first look at LUT-net. LUT-net replaces BNN's XNOR operations with learned K input Boolean operations that each get mapped to exactly one physical LUT on the FPGA. In the figure, 3 input LUTs replace the XNORs. X would be the input vector to the XNORs, and XR and XR prime are random selections with replacement from X. Therefore, in LUT-net, each input can participate multiple times in the weighted summation, and redundant operations can be removed with the help of network pruning. Compared to PolyLUT, LUT-net supports only binary inputs, and the number of trainable parameters scales exponentially with the number of LUT inputs. Moreover, LUT-net contains exposed data paths, and the design is bottlenecked by large adder trees. In contrast, LogicNet encapsulates inside a logical LUT all the operations that happen between the quantized inputs and quantized outputs of a traditional linear plus activation neuron, thus generating a netlist of logical LUTs. Moreover, LogicNet supports larger bit widths, and depending on its size, each logical LUT gets mapped to one or more physical LUTs by the synthesis tools. To address the exponential growth of the size of the truth tables, LogicNet uses high sparsity to reduce the high fan-in of each neuron. Our work PolyLUT utilizes the same a priori fixed sparsity technique as LogicNet. It is important to note, however, that a neural network consisting of linear layers and rectified linear units computes a continuous piecewise linear function. However, from the perspective of the RTL, the neurons are just lookup tables. So why should we restrict ourselves to only linear functions? Why not use a much more flexible function, such as a polynomial? Therefore, we suggest training continuous piecewise polynomial functions instead, with almost zero hardware overhead. Therefore, we expand on the idea of converting a neural network into a netlist of LUTs by exploiting the LUT's ability to implement a wide range of functions. We apply the polynomial transform inside each neuron by augmenting the feature space with all of its monomials up to a certain parametric degree d. In this figure, inside a neuron, we perform an expansion for a multivariate polynomial of degree equal to 2. When the degree is equal to 1, PolyLUT's behavior becomes linear, equivalent to LogicNet's. It is thus a strict generalization of LogicNet. We make available PolyLUT's toolflow, which contains the following stages. The first stage is the quantization-aware DNN training, for which we utilize a PyTorch framework. The next stage is the neuron-to-logical LUT conversion, which entails the generation of all possible input combinations based on their specified bit width, and then tabulating the neuron function evaluated on all of these combinations to construct their logical truth tables. Following this, the whole network is automatically converted to Verilog, and each truth table is written out as distributed read-only memories. The final stage in the pipeline is performing synthesis in place and root to generate the bit stream. Let's now visualize what the advantage of training piecewise polynomial functions looks like on something very small. For this, we train a 2-dimensional toy neural network in 2 different settings. The first setting is linear, equivalent to logic nets, and the second setting incorporates polynomial functions with degree up to 3. We train these networks on a fictional dataset of 2 spirals representing 2 classes, black and red. The formation of the piecewise functions can be visualized by looking at the output of each neuron. Looking at the final piecewise linear classification, we observe that 4 linear regions are insufficient to separate the data faithfully due to the high degree of overlap in the training data. In contrast, the piecewise polynomial surface can adopt more intricate shapes, enabling it to distinguish more complex data patterns with greater precision. However, a high-degree multivariate polynomial model introduces more degrees of freedom, which can lead to overfitting. To mitigate these issues, there are several regularization techniques that can be employed. For example, decreasing the degree of the polynomial leads to better generalization while maintaining the same number of logical LUTs. But we could also control the model's complexity through reducing the width or the depth of the network, which can lead to significant resource savings. Moreover, eliminating layers leads to a reduction in the number of clock cycles required to classify the input data, thereby improving computational efficiency. As a case study, we selected the jet substructure tagging task. This is a problem from CERN's particle accelerator, which requires ultra-low latency solutions. Enabling deep learning algorithms will allow the experiment to preserve potential new physics signatures related to Higgs and dark matter. For our experimentation, we trained the following 5-layer network using polynomial degrees ranging from 1 to 6. We have analyzed the effects of layer elimination by systematically removing each hidden layer at a time, generating a set of subnetworks that were also evaluated on the same range of polynomial degrees. By looking at the trends in training loss and test accuracy, the most valuable observation is that the performance boost achieved through polynomial function training is equivalent to adding more layers to a linear network. We observe that a 5-layer linear network yields nearly the same accuracy as that of a 2-layer polynomial network. Overall, we observe that the models with a degree equal to 1 are less efficient compared to all the other data points. There is a consistent improvement going from degree equal to 1 to degree equal to 2. However, as the degree is further increased, the improvements become less consistent, suggesting that very high degrees may bring diminishing returns. This can be explained by the fact that increasing the function complexity allows for better fitting of the data. However, larger degrees tend to be more challenging to train or can result in overfitting the training data. For the previous models, we have also analyzed the latency and the number of LUTs with their associated test error rates. It is evident that the Pareto frontiers of the polynomial design points demonstrate greater efficiency in the trade-off between latency and area versus test error rate, surpassing the performance of the Pareto frontier of the points with degree equal to 1. In our analysis, we have also observed that for higher polynomial degrees, slightly more physical LUTs are required for the same network topology. This is a direct consequence of the logical LUTs now being utilized to express more meaningful functions. However, the increase in physical LUT utilization due to increasing the degree is well offset by the reduction in the number of layers, overall leading to savings in the number of LUTs. We evaluated our approach on 3 different tasks. The first one is the network intrusion detection. The second one is the handwritten digit recognition using the MNIST dataset. And the last one is the jet identification at the CERN Large Hadron Collider. For similar accuracies, our method achieves significant latency improvements with reductions of up to 2 times, 19 times, and 4 times respectively. In this work, we introduced PolyLUT, a novel DNN hardware codesign methodology designed to meet the stringent demands of on-edge applications, specifically in terms of ultra-low latency and minimal area requirements. We've made the tool flow open source, so you can now download the code and try it out using the QR code or the link in the paper. We proposed mapping sparse and quantized polynomial neural networks to netlists of LUTs by training multivariate polynomials instead of linear functions. Thus, we leverage the capabilities of a LUT to represent any function, and we maintained accuracy on shallow neural network models. And finally, we have demonstrated the effectiveness of our approach on 3 different datasets. Thank you very much. I'm now open to answer your questions.